Hello everyone, welcome to Gate Academy Global. So now we will discuss about the different topics of eccentric loading in detail. Okay, so now the first type of loading is discussed here, that is eccentric load in plane of joint. So in plane of joint, if there is an eccentric load like this, so this is the connection. Let us say there are few bolts or screws like this. Okay, and this is the bracket which is subjected to an eccentric load. Okay, now the first of all in any numerical problem, okay, in any numerical problem there may be two situations in your GATE examination or different examination, that the centroid of the arrangement may be given or it may not be given. Okay, so if centroid of arrangement is not given, then what will be the situation? There may be a situation where the width of the plate, okay, width of the plate and depth of the plate will be given, and the relative positions of the bolts or screw will be given with respect to the different sides of the plate. Okay, like this will be given. Okay, this dimension will be given. Let us say this is h1. Okay, this is b1. Okay, this will be given. The distance between these will be given. Okay, so different things will be given. Now if the dimension of plate and the relative position, pitches, etc. are given in the question, then you can find out the center to center distance between the bolts placed in different rows and in same rows. Okay, now here you can see that after joining the center of the bolts or the screw, you will be having a geometric shape. Okay, now we have to find out the centroid first if centroid is not given. Okay, so if the area of each bolt is A equal to pi by 4 d square, okay, and if there is n number of bolts, so areas will be A1, A2, A3, A4 up to AN. Okay, now for locating the centroid we will have a reference axis like this. Okay, now with respect to the reference axis we will be locating the coordinates of center of each bolt. Okay, so let us say this is bolt number 1, this is 2, this is 3, this is 4. There may be more bolts and the different arrangements is also possible in case of a bolted joint. Now here the x coordinate will be like x1, x2, x3, x4 up to xn. That means the x coordinate of the bolts with respect to the reference axis. Similarly, y1, y2, y3, y4 and so on up to yn will be the y coordinate of different bolts with respect to the reference axis. Now if this can be calculated from the figure given in the question, then we can write the centroid as x bar equal to a1 x1 plus a2 x2 plus a3 x3 plus an xn up to an xn divided by a1 plus a2 plus a3, okay, plus up to an. Okay, this will be the x coordinate of the centroid, because the centroid will be having a coordinate of x bar y bar. So after finding x bar and y bar, we will be able to locate the centroid. Okay, so y coordinate can be written as a1 y1 plus a2 y2 plus a3 y3 plus up to an yn divided by a1 plus a2 plus a3 plus up to an. Okay, so on solving these relationships we will be getting the coordinates of the centroid. Once the centroid is known, then the second step is to locate the position of the bolts with respect to the centroid. So if G is the centroid, then we will be drawing lines, different lines joining the centroid and the center of each bolt like this. Okay, so this distance is R1, R2, R3, R4. Okay, so we can calculate R1, R2, R3 and R4. So G will be very important for calculating this distance. Now next thing, that is the next step will be, okay, next step will be calculation of primary shear force. Okay, primary shear force, as previously we have discussed that in such arrangement we can reduce the given loading condition, which is an eccentric load, into a load acting at the centroid of the joint and a moment acting along the centroidal axis of the joint, that is this. Okay. Now this load will be creating a primary shear force, okay, and the primary shear force in each bolt will be equal, okay, as this force is acting at the centroid, as the primary shear force will be equal. So P1 dash equal to P2 dash equal to P3 dash up to Pn dash, okay, will be equal to P by N, where N is the number of bolt or screw. Okay. Now using this we can find out the primary shear force. Okay. Now we have to calculate the secondary shear force. So before calculating the secondary shear force, we must calculate the radial distance of the bolt with respect to the centroid. Okay. So we will be calculate R1, R2, R3, R4 up to Rn, where N is the number of bolt. Okay. Now this can be calculated using simple analysis. Okay, simple trigonometrical analysis will be there in order to calculate R1, R2, R3 and different radial distances. Now why is it required? Because the secondary shear force, the fourth step, that is secondary shear force, that is P double dash is directly proportional to this radial distance R. Okay, the radial distance R. The analysis is very similar to the riveted joint. Okay. Now if you remove the proportionality, you will be having P dash is equal to C into R. Okay. Now if there are different bolts in the joint, then P1 double dash will be equal to C into R1, P2 double dash will be equal to C into R2. Okay, and this will be followed till nth number of the nth bolt. Okay, so Pn double dash will be equal to C into Rn. Okay. Now this secondary shear force is due to the moment. Okay, due to this moment acting about the centroidal axis. Okay, this is the centroidal axis perpendicular to the whiteboard. So the bolts must produce a secondary shear force, that is a resisting force which will be resisting the moment. Okay, so they will be giving a moment about the centroidal axis, and hence the external moment, that is P into, will be countered. Okay. Now using this concept, we can write that the moment of external force, the moment of external force will be equal to moment of resisting forces, resisting force. Okay, that is secondary shear force. Okay, so the moment of resisting forces or secondary shear forces is known as resisting moment. Okay, and this will be the algebraic sum of P and double dash into R and Rn. Okay, into Rn. Okay, so the algebraic sum of P and double dash into Rn will be giving you the value of secondary shear force, where n is equal to where the limit is from n is equal to 1 to n is equal to n. Okay. Now this is the resisting shear force, this is the resisting moment. Now the external moment is P into E. Now on solving this equation, we will be getting P into E is equal to P1 into R1 plus P2 into R2 plus P3 into R3 plus P1 double dash, P3 double dash, P2 double dash will be there. Okay, so P4 double dash into R4 up to P and double dash into Rn. Okay. Now from this relationship you can see that P1 double dash can be written as this, P2 double dash can be written as this. So replace the values from C into R. Okay, in terms of C into R, you can write that this will be C into R1 square, this will be C into R2 square, this will C into R3 square plus so on up to C into Rn square. Okay. So from here you can get the value of constant of proportionality. So this will be P into E divided by R1 square plus R2 square plus R3 square plus up to Rn square. Okay. So this will be the value of C. Now it is very clear from this equation. If you see very closely, then if there are number of bolts in the connection, then there will be a large value in the denominator. Okay, then what will happen? Then this value being high, we will be getting a smaller value of C. Okay, if this entire terms is high, then definitely C will be low, and the term will be high only if there is very large number of bolts in the joint. So if there is very large number of bolts in the joint, then this term will be very high, hence C will be very low, and if C is very low, then definitely secondary shear force is very low. So if you want to reduce the value of secondary shear force, then you must increase the number of bolts. So on increasing the number of bolts, what will be the consequences? If you increase the number of bolts, then the primary shear force will also reduce and the secondary shear force will also reduce. Okay, so note it down that on increasing number of bolts, okay, the primary shear force as well as secondary shear force will decrease. Okay, now as soon as we get the value of C, we will be able to calculate the values of secondary shear force. So secondary shear force that is P1 double dash, P2 double dash, P3 double dash and P4 double dash will be equal to P into E divided by R1 square plus R2 square plus R3 square plus R4 square multiplied by R1. This will be equal to P into E divided by R1 square plus R2 square plus R3 square plus R4 square into R2. This will be P into E divided by R1 square plus R2 square plus R3 square plus R4 square, okay, multiply by R3. This will be P into E, okay, divided by R1 square plus R2 square plus R3 square plus R4 square. Okay, as in the connection given in the example, okay, we have only 4 bolts, so I am writing up to R4 only. Okay, there can be more bolts in the connection, so multiply by R4. Okay, now as I have told you the direction, this is the centroid of the connection, then this will be the direction of primary shear force. This is 1, this is 2, this is 3, this is 4, this is P1 dash, this will be P2 dash, this will be P3 dash, this will be P4 dash. Okay, and this is the line joining the center and the centroid of the arrangement. Okay, this is center of the bolts, this is the line joining center and the centroid of the connection. Okay, so the secondary shear force will always act perpendicular to this line, so this will be P1 double dash, okay, this will be P2 double dash, okay, this will be P3 double dash and this will be P4 double dash. So as you can see, all these secondary shear force are causing an anti-clockwise sense of rotation, okay, and they will be causing a moment equal to P into E. The moment of the secondary shear force about the central axis has a magnitude of P into E. And why is it so? Because this equation is being followed. Okay, condition of static equilibrium. This equation is from the condition of static equilibrium. So summation of moment about the centroid will be equal to 0. Hence, this equation will be obtained. So you can see that the resulting moments are also having a magnitude of P into E. Okay, so this will be the direction of primary and secondary shear forces. Okay, now here the angle between the primary and secondary shear forces is, let us say here this is theta, this is theta 2, this is theta 3 and this is theta 4. Now theta, the value of theta is to be calculated. So next step is calculation for theta. Okay, so theta 1, theta 2, theta 3, theta 4 up to theta n can be calculated by using simple trigonometrical analysis. So this value will be coming out from the trigonometric analysis. Okay, now after calculating theta, we will be calculating resultant shear force. Okay, so resultant shear force R can be written as root over P1 dash square plus P1 double dash square plus 2 P1 dash double dash cos theta. So for any bolt, okay, you can use the formula. So this you can also write it as Rn. Rn means for any nth bolt. For first bolt this will be R1, for second bolt it will be R2. Okay, here also we can write n. Okay, theta n. Okay, so let us write for the bolt number 1, that is R1 will be P1 dash square plus P1 double dash square plus 2 P1 dash P1 double dash cos theta 1. So similarly you can find out R1, R2, R3, R4, and if there are n number of bolts you can find out up to Rn. Now the most high value will be the greatest value of the shear force. Okay, so the resultant shear force, or simply the shear force on the bolt, is the resultant force. Okay, now the bolt which is having the highest value of resultant force is known as the critical bolt. Okay, so critical bolt, it is bolt with highest value of resultant shear force. Okay, this is the bolt with highest value of resultant force. Now for the critical bolt, after calculating that which is the critical bolt, okay, so the shear stress is maximum for the critical bolt. Okay, now we have seen that the calculation for shear in your gate examination or engineering services examination or different competitive examination will be based on the shank diameter, that is the major diameter of the bolt. Okay, because in order to solve the problem based on the core diameter, we must have a manufacturer catalog so that we can refer to a proper value of major diameter. So here, as you can see that there will be two possibilities in case of shear. The shear can take place at the shank and at the thread portion as well. So for gate examination and engineering services examination and different examination like this, you will always assume that the shear is taking place at the strongest portion, that is the shank portion. So the shank portion will be subjected to shear. So this shear stress will be acting on the shank portion. Although it is very useful to design the bolts or the screw for the minimum area, that is for minimum area the stress will be acting at the core area, that is the area based on core diameter of the bolt. Okay, but if core diameter is calculated, then finding the major diameter based on the value of the core diameter requires a manufacturer catalog or some empirical relation based on the type of thread being used in the bolted connection. Okay, so that's why for safer side we will always consider that shear is there in the shank portion, and as the shear is in shank portion, then we will be having the value of major diameter always. Okay, so we will always have the value of major diameter. Now so if D is equal to the major dia, or you can call it nominal dia, okay, nominal dia, then tau max will be R max, that is the maximum value of resultant force, that will be on the critical bolt, okay, divided by pi by 4 d square. Now this should be less than or equal to tau permissible. Okay, now tau permissible can be written as SYS divided by factor of safety. Okay, SYS is the shear strength or yield shear strength of the material of the bolt. Okay, now here at this stage we can use different theory of failures. That means either we can use MSST, that is maximum shear stress theory, that suggests that SYS will be equal to 0.5 times of SYT, or we can use MDET, that is maximum distortion energy theory, which suggests that SYS will be equal to 0.577 times of SYT. Okay, and with help of these two theory of failures, and after using a proper factor of safety, we will be able to use the know the value of permissible shear stress, and hence on using limiting condition we will be able to solve the problem. So in limiting case this tau max, that is R max divided by pi by 4 d square will be equal to tau permissible. Okay, and I was solving this problem, this equation basically will be having the value of nominal diameter. Okay, that is the least diameter required to sustain this load. Okay, and hence the problem will be solved. Also, if the diameter is known we can calculate the stress, we can calculate the shear force in the most critical bolt. Okay, so this will be the design procedure for the eccentric load, where the eccentric load is placed in a plane of joint. Okay, now let us see the next type of eccentric loading. Now we will see a second category of eccentrically loaded bolted joints or threaded joints. Okay, where the eccentric load is parallel, is in a plane parallel to plane of bolts. Okay, also you can call it the line of action of load. Line of action of load is perpendicular to centroidal axis. Okay, so here we will have a situation like this. This will be the wall, this will be the base plate of the bracket. Okay, here we will be having an eccentric load. This is the centroid of the connection. Okay, this is the bolt. Okay, this is the bolt. Okay, and we have discussed the concept previously. Okay, so now the design part will be discussed. So this is the lower edge, this is the lower edge. Okay, this is the lower edge. Now let us consider that the distance of the axis of bolts with respect to the lower edge is like this. This is the bolt number 1, and there is another bolt which we cannot see. Okay, you have seen these cases in previous lectures as well, so I am not telling everything in detail. We will discussing the design part only. Okay, so we will have a bolt number 1 and 3 here, 2 and 4 in this row. Okay, we can have more number of rows, okay, and more number of bolts in a row as well. Okay, so the fundamental procedure will remain same. Okay, so this load will be transferred at the centroid. Okay, and it will be creating a moment of P into E. Okay, and E is the eccentricity of the load. E is the eccentricity of the load. Okay, now here the distance of first load, that is L1. Okay, and this is L2. Again here in majority of cases the centroid of the arrangement will be mentioned. Okay, and if it is not mentioned, then also there is no need to calculate the centroid. Okay, all we need to have is the centricity, okay, and the position of the various rows of bolt with respect to the lower edge. That means the value of L1 and L2, and if there is 3 rows, so L1, L2, L3, L4, these values are more important. Okay, the radial distance, that is R1, R2, R3, this is not important, because here we will be having two types of stresses. One is the direct shear stress and second is the tensile stress. Okay, we have discussed everything in detail in previous lecture. So now the direct shear stress, that is primary shear force will be P1 dash equal to P2 dash equal to P3 dash equal to P4 dash, because here we will always assume that this load is acting exactly perpendicular to the centroidal axis. Okay, hence the load will be equally distributed among the number of bolts, okay, or the number of screws. So this will be equal to the applied load divided by the total number of bolts, that is N. Okay, so from that relationship we will be having the value of primary shear force, or you can say the direct shear force. Okay, direct shear force, which will give you a direct shear stress. Okay, now as you can see that this is the external moment, and these bolts will try to resist the rotation. Okay, this will try to resist the rotation. Hence we can write the external moment P into E is equal to the resisting moment, and resisting moment can be calculated very easily. Let us say here we have resisting forces as P1 and P3. okay, and here we have resisting force of P2 and P4, okay. So from here we will be having P1 into L1 plus P3 into L1 plus P2 into L2 plus P4 into L4. Also the normal force, that is P1 double dash, okay, this is the normal force acting on the bolts. So this P double dash is normal force, okay, normal force acting on bolts, okay. Now this normal force is directly proportional to the distance from the lower edge, okay. So P1 double dash will be equal to C into L1, P2 double dash will be equal to C into L2, P3 double dash will be equal to C into L3, P4 double dash will be equal to C into L4, and so on, okay. So from here we can write the value of C, okay, after taking common, as equal to P into E divided by L1 square, okay, plus L2 square plus L3 square, okay, plus L4 square, and so on up to Ln, okay, Ln square. So this will be the value of C. Now as soon as we get the value of C, we will be able to calculate P1 double dash, P2 double dash, and P3 double dash, okay. So we will be calculating these values, that is the tensile force, okay, tensile force, okay. P1 double dash will be equal to P into E divided by L1 square plus L2 square plus L3 square plus L4 square, okay, multiplied by L1, okay. P2 double dash will be P into E divided by L1 square plus L2 square plus L3 square plus L4 square multiplied by L2. P3 double dash will be equal to P into E divided by L1 square plus L2 square plus L3 square plus L4 square multiplied by L3. P4 double dash will be P into E divided by L1 square plus L2 square plus L3 square plus L4 square multiplied by L4, and it will goes on, okay, up to P n double dash, okay. This will be same, okay. If there are n number of ports, so this will be L1 square plus L2 square plus L3 square up to L plus Ln square multiplied by Ln, okay. Now this tensile force will give you tensile stress, as we have discussed earlier, okay, tensile stress, and this will give me shear stress or direct shear stress, okay. Now the tensile stress on the bolt, now here comes the problem, as I have told you earlier, that in tensile loading we may consider the core diameter, okay. So when a bolt is subjected to a direct tensile force, so in that case we will majorly consider the core diameter, okay. But if the data is not given like that, so in that case we may consider the shank diameter also, but for majority of cases where there is a tensile loading in the bolt, then we will be considering the core diameter, because in tension the core area will be the critical area at which the maximum stress will produce, okay. Now here, as the shear stress is being analyzed in the shank portion, so it becomes mandatory to solve the problem for the shank area only, okay. So we will be solving the value of stresses, that is tensile stresses and shear stresses for the shank area, and if in the question it is required to calculate the core diameter or the core area, then we will be proceed accordingly. That means we will use the core diameter for our calculation, okay. So if it is mentioned in the question or if it is asked in the question, then we will be going for the core diameter. Otherwise we will be using the nominal diameter for our calculation, okay. So this tensile stress sigma will be equal to P double dash divided by area, that is pi by 4 d square. D is the nominal diameter, this is the nominal diameter, okay. Now we can calculate the shear stress, okay. So shear stress, that is tau, is equal to P dash divided by pi by 4 d square, okay. Again this is the nominal diameter, or we can go for DC also, okay. DC can be used if required, and this requirement will be based on the question. If this is not in the question, we will definitely go for the nominal diameter, okay. So according to this, we will be having the values in terms of diameter only. Okay, we will be having the value of P dash, we will be having the value of P double dash, and the stresses will come in terms of diameter only. Okay, so the principal stress or the maximum shear stress will come in terms of diameter only. Clear? And then on using the failure criteria, we will be having the value of diameter. This is the fundamental idea. Okay, so the state of stress will be like this. This is the tensile stress, value will be equal to P double dash divided by pi by 4 d square. Okay, and here we will be having direct shear stress. Okay, direct shear stress, and this will be equal to P dash divided by pi by 4 d square. Okay, now we can write the value of principal stress, maximum principal stress. Okay, maximum principal stress, okay, that will be equal to sigma max will be equal to sigma by 2 plus root over sigma by 2 whole square plus tau square. Okay, this will be the maximum principal stress. If we want to calculate sigma minimum, so this will be sigma by 2 minus root over sigma by 2 square plus tau square, and definitely it will be 0. Definitely it will be 0. There is no doubt that it will be 0, because if you draw the Mohr circle for the same, then you will be having the value like this. Okay, this state of stress may be indicated over this point. I am drawing a rough diagram only. Okay, there is no need to put more time in this discussion, because I think you will be confident enough to analyze such situation. Okay, if this is plane A, so this will be plane A. Okay, and this will be plane B. Plane B is having 0 normal stress and a shear stress, so this will be 0 normal stress and a shear stress, so this will be the Mohr circle. Hence you can see the intersection points of the Mohr circle. So this is a positive value of the principal stress, and this indicates a negative value of the principal stress, and it is the negative value, and being a negative value, so according to our consideration, the minimum principal stress will always be a negative value in case of in case of any loading. Okay, so here you can see is, as this is a case of plane stresses, so stress along this direction will be 0. And the maximum principal stress is coming out to be maximum principal stress is coming out to be positive, and the stress in the direction perpendicular to the plane is 0, and the last stress is coming out to be negative. So one value is positive, another is 0, and the last one is negative. So according to the algebraically highest and largest concept, this will be the maximum value and the negative one will be the minimum value. So this will give you a negative value. This will be negative definitely, and hence this will be sigma 3. This will be sigma 3 and this will be sigma 1. Okay, and if you want to calculate the tau max, so tau max will be equal to sigma max minus sigma minimum divided by 2. Okay, and this will be the absolute maximum shear stress, or you can also solve the formula, that is sigma by 2 whole square plus tau square. This will be your tau max absolute. Okay, this is the concept which have been discussed previously also. Okay, now we can use the different theory of failures. Either we can use the Rankine's theory. So according to Rankine's theory, we will be using for Rankine theory, okay, that is maximum principal stress theory, MPST, maximum principal stress theory. This sigma max should be less than or equal to sigma permissible. Okay, so this will be sigma max should be equal to, for limiting case, this should be equal to sigma permissible. Okay, and this will be equal to SYT divided by factor of safety for a ductile material, or if it is a brittle material, which is not possible actually, but if it is a brittle material, then it will be SUT divided by factor of safety. And on solving this equation, as this sigma max will be in term of D, solve this equation and get the value of the diameter, that will be the nominal diameter. And then we can also apply MSST. So what kind of theories to be used will be given in the problem, or the permissible stress will be given in the problem. So if the permissible shear stress is not given in the problem, then we will be going for the different theory of failures. Okay, so a theory of failure will be mentioned in the question, or directly the value of permissible stresses will be given in the question. Or also, if the theory of failure is mentioned, then you will be needing the value of strength of the material. So there you will find the value of yield strength of the material and factor of safety. Okay, and if the theory is mentioned, then you will be using this formula which I am telling you. If MSST is mentioned in the question, then the tau permissible will be equal to SYS divided by factor of safety, and here SYS will be equal to 0.5 times of SYT. And if MDET is mentioned in the question, then tau permissible will be equal to SYS divided by factor of safety, and SYS will be equal to 0.577 times of SYT. This will be the relationship. Now for design for safety in shear, if you want to design safe, if you want to make a design which is safe in shear, so for safety in shear, the tau max absolute should be less than or equal to tau permissible. Okay, and you will be having two options, either this or this, to solve the problem. Okay, and use limiting condition. In limiting case, tau max absolute will be equal to tau permissible, and on solving this equation you will be getting the value of nominal diameter. And if the calculation is for the co-diameter, then you will be getting the value of co-diameter. So this will be the procedure. What are the different types of stresses, how they are coming, has been discussed previously. I think there will be no doubt after watching all these lectures. Okay, so this is the proper procedure which is to be followed for this type of eccentric loading. Now let us see when the eccentric loading is parallel to the centroidal axis of the connection. Now we will see the third case of eccentric loading. Okay, so here, as I have told you earlier, that the line of action of load, okay, will be parallel to this centroidal axis. This is the centroidal axis. Okay, now here we have bolts. Now we have discussed that if this is the eccentricity, then this load can be replaced. Okay, I am replacing this load like this. It will be transmitted to the centroid, and due to eccentricity we will be having a moment M is equal to P into E. Okay, now let us replace this load completely. Okay, so after completely replacing it, as the load is now acting at the centroid of the connection, then this load P will be distributed equally among the rivets. Okay, this will be distributed equally among the rivets because it is being acted at the centroid. Okay, so the tensile force, basically tensile force, or you can say direct tensile force will be given as P1 dash equal to P2 dash equal to P3 dash equal to P4 dash up to Pn, okay, equal to P divided by the number of bolts. Okay, now here also we don't need to calculate the radial distances of the center of the bolt and the centroid. Okay, now this is the lower edge, okay, let us see, this is the axis of the bolt. So this distance is L2, this distance is L1. Here we have four bolts in the arrangement. Okay, so here is bolt number 1, and just right next to it we have bolt number 3. This is bolt number 2, and right next to it we have bolt number 4. Okay, so we have basically 4 bolts in the arrangement. There can be more bolts, there can be 2 bolts only. Okay, but situation will be like this. So let us understand the next step. So after this, you can see that due to this moment P into E, the arrangement will try to tilt, and this tilting will be resisted by the bolts itself. Okay, then the bolt will be subjected to a tensile force due to this moment. Okay, so to resist this moment, which is trying to rotate the bracket about the lower edge. Okay, we will be having some tensile forces, okay, as the reaction forces. Now the moment of reaction force that is tensile in nature basically is equal to external moment. Now you may get confused that as this is the moment acting at the centroid, okay, then how can we equate this value, because this is the moment, the moment of the resisting force is about the lower edge. So the thing is, this is acting in the bracket, okay, and this is a moment of force, this is not a force. If there is a force, then the moment of the force about the lower edge will be different, but this is the moment, and we don't have to consider the moment of the moment again, so we don't have to multiply it by the distance. So the location at which it is acting is not necessary. So basically what will we do, we will do the summation of moment about the lower edge equal to 0, okay, and about the lower edge, this is the moment, okay. So we will only consider the sense of rotation, and from this we will be having the equation, that is moment of resisting force, okay, will be equal to the external moment about the lower edge. LE means the lower edge, okay. So from here we can write P1 into L1, okay, plus P2 into L2 plus P3, sorry, P1 double dash, P2 double dash, P3 double dash into L3 plus P4 double dash into L4, and so on up to Pn double dash into Ln is equal to P into E, okay. Now as you can see that here the bolt which is far away from the lower edge will be having more tensile force, okay. That means the P double dash will be directly proportional to L, hence P double dash will be equal to C into L, okay. So P1 double dash will be C into L1, P2 double dash will be C into L2, P3 double dash will be equal to C into L3, and P4 double dash will be C into L4. So put these values in this equation, then you will have C into L1 square plus C into L2 square. So let us take C as common. So C into L1 square plus L2 square plus L3 square plus L4 square, and so on up to Ln square is equal to P into E. So we will be having the value of C as P into E divided by L1 square plus L2 square plus L3 square plus L4 square plus so on up to Ln square. This is the value of C. So now we can have the value of the tensile force, okay, that may be that can be also called as indirect tensile force or the secondary tensile force, okay. So this is also a tensile force. So P1 double dash will be equal to P into E divided by L1 square plus L2 square plus L3 square plus L4 square up to Ln square multiplied by L1, okay. Now as L1 is greater than L2, then definitely P1 double dash will be having a value higher than P2 double dash, okay. Also L1 is equal to L3, hence this will also be equal to P3 double dash. So P2 double dash or P4 double dash will be same, and this will be PE divided by L1 square plus L2 square plus L3 square plus L4 square up to Ln square multiplied by L2, okay. If there are more number of bolts in the arrangement, there will be more terms, okay, but the concept, the idea will be same, okay. Now both these stresses, both the loads are tensile loads or tensile force, and both will cause a tensile stress in the bolt, okay. So the stress due to the direct tensile force will be equal to P dash divided by pi by 4 d square. Here also we will consider the nominal diameter if nothing is given in the question. If it is asked to calculate the core diameters, then P dash upon pi by 4 d square, or we can also calculate the stress based on the core diameter by using the relation, that is P dash upon pi by 4 dc square. It is advisable that for a tensile load, the calculation should be based on the core diameter, okay. So if the data is such and the question demands like this, then you can go for the core diameter, okay. Now for the secondary tensile force, that is P double dash, we will have another tensile force, that is tensile stress, that is pi by 4 P double dash upon pi by 4 d square, or in terms of the core diameter we will have P double dash divided by pi by 4 dc square, okay. So let us say this is sigma T1, this is sigma T2, this is for the first bolt, okay. And the first bolt, that is the bolt which is at a higher distance with respect to lower edge, will be having the higher value of secondary tensile force, okay. Hence the resultant force will be high for the upper row of the bolts, okay. So note it down that resultant force will be higher for upper row of bolts or screw. Hence, if I ask you which one will be the critical bolt, so the bolt number 1 and bolt number 3 will be the critical bolt, as the resultant force will be high in case of the bolt number 1 and bolt number 3. Okay, the direct tensile force is same in all the bolts, but the secondary tensile force that is indirect tensile force is high in the upper row of the bolts. Okay, so the resultant will be high in the upper row only. Okay, so we will be designing for the critical bolt. Okay, so for critical bolt, resultant force will be maximum. Resultant force will be maximum. Okay, resultant force will be maximum. Okay, so the resultant force in any of the bolt, resultant, as both are tensile in nature, will be equal to P dash plus P double dash, or you can write Rn, that is resultant force in any nth number of the bolt, will be equal to Pn dash divided by P plus Pn double dash. Okay, so if you talk about bolt number 1, so for bolt number 1 you can write, you can also write R1 will be equal to P1 dash plus P1 double dash. So this will be the resultant tensile force, and hence the maximum tensile stress will be equal to sigma max R1, okay, or you can write R max, that is the maximal resultant force, divided by pi by 4 d square or pi by 4 dc square if the calculation is for the co-diameter of the bolt. Okay, now this should be less than or equal to sigma permissible, that is the permissible tensile. Sigma permissible is permissible tensile stress. So for safety, this condition should be followed, and we will use limiting case or limiting condition in order to solve the problem, that is sigma max equal to sigma permissible. So we will equate R max divided by pi by 4 d square, or you can write R max divided by pi by 4 dc square is equal to sigma permissible, or sigma permissible can be written as SYT divided by factor of safety, SYT divided by factor of safety. Okay, so on solving this equation, if we have to calculate the nominal diameter in the problem, then we will be getting the value of nominal diameter, and if we have to calculate the core diameter, then we will be able to get the core diameter. Now if there is some doubt that how we can get the nominal diameter from the core diameter, then let me tell you the relationship, that is DC will be equal to 0.8 times of D for a metric thread, Okay, so if the thread is metric thread and we have to calculate the nominal diameter from the core diameter, or core diameter from the nominal diameter, then we can use this equation for our solution. So this was the complete discussion about eccentric load in a threaded connection. I hope you have understood everything in very detail. Thank you.